Okay, here's a quick kinetics problem, sort of building on what we talked about gears, about the kinematics of gears. Here's a quick question. Say a motor at O1 was applying a moment M1 K at O1, okay, where uh, a moment, or what I mean by a moment is basically a torque, where M1 is known. Um, let's say the gears are rigid bodies, as we know, or as we assume, with moments of inertia I1 and I2 respectively, let's say. About O1 and O2 respectively. And then the question, the setup is basically the same as this. Determine the angular acceleration alpha 1 and alpha 2, okay, of the two gears. Um, gear 2, so this is the question, gear 2 has no friction or moment at O2, okay. So you asked to find, so what's given is that there's a moment, there's a torque at a point O trying to rotate this gear, and because this gear rotates and has some angular acceleration, this gear will have an angular acceleration as well, and you're asked to find what the angular accelerations are of these things. You're told the moments of inertia and so on. What's the first step? The first step is to draw a free body diagram of the gears. Let's ignore gravity. We can add them if we want, but this is gear 1. We have some reaction forces. And we have some moment here, M1, about this point. And then at this point, we have some force, let's say, that's acting like so, F. Okay. That's the force of contact between the two gears. Now, gear 2 is like so. it's got reaction forces ry2 rx2. I said ignore gravity, but doesn't really matter. You can add gravity as well. It has no import on this problem. M2G if you want, if the masses are known. And then at this point, we have an equal and opposite force. Because these 2 points are in contact, they will have the same force but equal and opposite. Okay, and that's the free body diagram, and we've been told that there's no friction or another torque here. Those are the free body diagrams. So what do we have? We have maybe alpha 1 like so, alpha 2 like so. By our convention, we can do sum of moments about O1 equals we can just do scalars if we want, or vectors, doesn't matter. I1 alpha 1 k, sum of moments about O1. This is for rigid body 1, for gear 1. So what are the moments of about this point for this? It's going to be m1 plus f1 f r1 equals I1 alpha 1. So that's equation number 1 that we have. And then for gear 2, so of course this is gear 1, this is gear 2. For gear 2, we have essentially F times R2, again anticlockwise, equals I2 alpha 2, equation number 2. There is this force F, which is the transmission force between the two gears, but you do not know what it is, and we have these two equations. So 1 and 2 have 3 unknowns. Namely alpha 1, alpha 2, and the contact force F. A third equation, need a third equation. But of course, we already have that equation. It's basically this equation. The angular accelerations are related by the ratio of the radii. Which is alpha 1 by alpha 2 equals minus R2 by R1, or okay, so we also have that. We can solve these 3 equations to solve for everything that we want. Let's first eliminate F from these 2 equations. Let's solve for from 2 we have F equals I2 alpha 2 by R2. Use this in 1, we get M1 plus F. For instead of F, we plug in I2 alpha 2 by R2 times R1 equals I1 alpha 1. And then we plug, let's call this 4, plug 3 and 4. 3 implies alpha 1 equals minus alpha 2 R2 divided by R1, and then we plug that into 4. Now, plugging 3 in 4, so plugging 3 in 4 like so, we get the following expression. So let's just do that. M1 plus I2 alpha 2 by R2 R1 equals I1 minus alpha 2 R2 divided by R1. Let's we see that there's alpha 2 here, alpha 2 here. Let's put them together on the same term. So we have M1 plus I2 R1 divided by R2 alpha 2 plus alpha 2 I1 R2 divided by R1 equals 0. So what do we have here? We have M1 equals minus alpha 2 I2 R1 by R2 plus I1 R2 by R1, which you can simplify further if you wanted, to alpha 2 I2 R1 square plus I1 R2 square divided by R1 R2. Okay. So that's it. So we have alpha 2 equals minus M1 divided by this whole thing. So we have I2 R1 square plus I1 R2 square times R1 R2. So that's going to be your alpha 2. And then we can quickly compute alpha 1 by using equation number 3. Alpha 1 equals minus alpha 2 R2 divided by R1. That gives us minus this whole thing. That whole thing, that's alpha 2 times R2 by R1. The R1s get cancelled here, and the negative signs get cancelled, so we have M1 times R2 square divided by I2 R1 square plus I1 R2 square. You can bring the R2 square to the denominator, and we would get M1 divided by I2 R1 square by R2 square plus I1. Okay, so this is the answer for alpha 1. Alpha 1 equals M1 divided by I1 plus I2 R1 square by R2 square. And these two things are the final answers. And let's examine this final answer for a moment. We say alpha 1, the angular acceleration of the first gear, is moment on that gear divided by this quantity, which has an I1 and then another term, right? So let's look at the picture again. If all you had was this gear and then it was not coupled to this gear, then the angular acceleration of this gear would be just moment m1 divided by I1 of that gear. But what happens is that when this gear is coupled to this other gear with a different moment of inertia and a different radius, then what it looks like is the angular acceleration of the first gear is not m1 by I1, but m1 by I1 plus another quantity. So it's as if you try to turn gear 1 with a moment m1, the inertia that you feel is not just that of gear 1, but also part of gear 2. So you feel that extra inertia of gear 2 as well because you're turning gear 2 as well, and this is how it gets reflected. And in fact, this extra term is called reflected inertia of gear 2, I guess, this term. Okay. In any case, it's as if the system has more inertia than just gear 1, which of course is true. Um, I guess we'll stop there.